Alright, let's talk about the damped pendulum model, and later we will be focusing on the nonlinear driven and overdamped case. And here's the table of contents. Let's talk about the modeling first. So here's a figure I drew, and then this is the equation or the model or the system. So let's talk about these three terms, four terms. So the first term here is the inertia term, and then B here is actually the damping term or friction, one could call. The mgl sine theta is actually the gravity term. Mg we'll go to it later. And then F here is the external torque, where I will call it forcing later, where I will just call it forcing. And then I'm modeling F as a function of T and X, where X is actually, I'm placing every other factor that can actually affect our system into just that vector X. Yeah, and then here's all of the constants and variables. Yeah. So let's derive the model, right, real quick. So let's consider a case where we have a simple pendulum where there is no external torque and no damping, and we can apply force analysis onto this pendulum here. So there's no external torque, no damping, therefore the whole pendulum is just only affected by gravity, mg. And then we know that we can split the forces into, well, orthogonal vector parts, and therefore we have the tangential gravity, well, that makes the most work, I guess, to be mg sine theta. And therefore by Newton's law we have this. And also note that a here is actually the acceleration of this axis only, and it is not the angular acceleration. However, we can relate them by using the arc length formula, which is this: S equals L theta. Differentiate them with time once and twice, we get this. Therefore we take this and put it back into here. We get this, where this is actually saying that where this is actually the equation of forces. But eventually we want to deal with torques instead. Therefore by the definition of torque, which is force times the length of, well, to the mass point, I guess, which is L here, so we just multiply everything by L, and then we get this equation where it describes the torque balance instead. Right. So okay, so we have derived the model for a simple pendulum without forcing or damping. Now let's just put them in, right? And here we will assume from the classical mechanics sense, and we assume that damping is directly proportional to angular velocity, so the faster it's going, the greater the friction, in a sense, and therefore the damping term will be given by B theta dot. And therefore let's just throw the damping and forcing back into the model. Therefore we have added these two terms in, and moving them to one side, we have exactly this will be our equation system model. Yeah. Now let's analyze this. Now let's look at this model real quick, right? It is a second order. It is non-linear because of this sine term, and maybe this x, well, technically we could have theta inside x, who knows. And then it's non-homogeneous unless we have f equals to 0, but even if f is equal to 0, we still have this non-linear term, which is bad. So it's hard to solve or even study, yeah. But you can find workarounds, or we can find ways to work around it. So one of the most known way to do it is in ODE classes. Normally we just consider linear case by using the fact that this sine theta is approximately theta for small values of theta. So we turn this into theta, and then now we have a second order linear if this forcing is great, is good enough. And then we can solve it. We have method of coefficients, variation of parameters, or Laplace transform, I guess. But yeah. Then here's 2, which is the one that we will be talking about, but let's talk about it later. I will reintroduce it later. And then 3, well, this is what I thought of, like when in doubt, I guess just brute force it via numerical methods, right? Then here's a remark that yeah, so note that the general damped pendulum system can actually become chaotic if our approximation sine theta is approximately theta fails. It's basically like there is a bifurcation from non-chaos to chaos, I guess, and you can find that in the footnote here. But anyways, okay, now let's go to our main focus of the talk. So for sake of simplicity, we'll focus on this case, and which we will be assuming that the forcing term is constant, and we will denote it by gamma. And then when we have and by overdamping, overdamping means we damped really hard, we damped a lot. Therefore, when we damp sufficiently large, we are damping such that the initial term is negligible. You can think of it like we have the pendulum, and then the pendulum at the point at the ground, I guess, the point there, we have some very viscous liquid. Viscous as in like it's very dense, sticky. In a sense, we could think of it as it is honey, very sticky honey, and therefore when it goes down, when it almost reaches 0, the honey is going to make it so that the pendulum is can't really move that much. It's very slow, and then our external torque, which is constant, it will try to push it through. Yeah, but basically in this case, because inertia is basically the force that tries to resist change, but here there's nothing too much to change in a sense. Therefore, the inertia term is negligible compared to the damping term, because the damping term basically makes all of the resistance here, in a sense. Yeah, but yeah, therefore we can simplify our model to this, and now let's analyze it. Okay, before we analyze it, it's normally a good idea to non-dimensionalize your equation so that it becomes easier to solve. By non-dimensionalizing, I mean that we are making like some substitution of variables such that our equation becomes something easier to deal with. Also note that here theta prime is written theta prime instead of theta dot. Is because we are changing, we are basically scaling time differently in a sense, and therefore we are writing it like this instead. Also note that let's say about this one first. Let's note that this small gamma here is equals to big gamma was mgl. We can also write it as 1 over ml times gamma over g. So ml are constants, so they are just like some scale factor. But note that big gamma and g is the gravity, and then gamma here is our external torque, and this will come into play real quick in a bit. And also I think it's fine. Okay, now let's talk about what happens to the system. So let's write down the system again. So it's theta dot equals to gamma minus sine theta, and gamma is given by 1 over, well, basically let's just ignore the constants because they don't do anything, which is given by the torque over G. So, see, for gamma greater than 1, what will happen is, so gamma greater than 1 means this term here, the external torque is greater than the gravitation, than gravity is always greater than it, in fact, and therefore it will just keep spinning counterclockwise. It will be slower in this part because of because of our equation here. Because when theta is from 0 to pi, sine theta is positive. From, well, basically this pi here is, we are basically connecting, we are pasting minus pi and pi together, in a sense. So from this part instead, you can think of it as like it's minus pi to 0. Where minus pi to 0, sine theta would be negative, and therefore theta prime here is instead positive. And therefore it will be way faster around here. Oh, I might have, let me write it back real quick. So theta prime because gamma minus sine theta, and then gamma is equals to tau, no, big gamma over G. So now when gamma approaches to 1 plus, well, 1 from the right side, meaning that if gamma is like 1.00001, 1 and maybe 1.000000001, basically it's very close to 0, but very close to 1, it's going to react the same way. Well, the system is going to work about the same way as gamma is greater than 1. However, the interesting part is when it's near pi over 2, because at near pi over 2, sine theta here will be an extrema. So it's the greatest there, and then gamma is, well, just a little bit greater than 1, where sine is 1, and therefore at this point it's going to be very slow, and it's going to be as if it's stopping there, but it doesn't stop instead. And instead, the moment it gets through the moment it reaches pi over 2 and gets through it, it will start accelerating again. And yeah, then gamma equals to 1. When gamma equals to 1, we have the torque equals to G. I mean, if this equals to 1, therefore the torque and gravity is going to be working about the same, inputting about the same power. But let's look at it from the equation, right? At pi over 2, we see that sine theta is actually equals to 1, and then gamma is equals to 1. Therefore, at pi over 2, it's our theta prime is equals to 0. And basically, we can also show that at pi over 2, it's a fixed point. Well, basically, because theta prime equals to 0, and therefore that point is a fixed point. And in fact, that point is a semi-stable fixed point, where we can show, but it's going to be quite obvious. Now, here are the more interesting cases. So, if gamma is less than 1, on the left side, it's going to be always turning the same way, but on the right side instead, we now see that we have two fixed points instead. So what happened here is that, think about it this way, right? Because gamma is less than 1, therefore it's basically saying that our external torque is inputting less power than gravity. So our torque is constant, and gravity can change because of the vector decomposition, right? So where is gravity strongest at? It will be this point, because gravity is exactly going down. At other points, it's going to be decomposed into the tangential parts, right? So this point would be a stable would be a stable fixed point because the constant torque is pushing it towards pushing it counterclockwise, and then the gravity is well, when it's going counterclockwise, gravity increases, therefore pushing it back down, and therefore, well, the pendulum can't really go anywhere, right? It's stuck in the middle of them, and therefore it becomes a stable fixed point. But this point, however, is unstable because the torque is constantly pushing it this way, and gravity is trying to pull it down. So let's say we kind of nudge our pendulum a little bit to the left. If I nudge it to the left, gravity actually becomes less gravity imposes less strength on it. Therefore, the torque, well, it's constant, right? Therefore, our pendulum will just move instead of just staying there, and therefore it becomes unstable there. So, and note that when gamma goes close to 0, our two fixed points, they will move further and further away from each other, and and then the stable one will go almost to 0, and the unstable one will go to pi, in which we can see it's just this case. we just go to here, and when gamma is equal to 0, basically this is 0. So we are and then at this case we have no torque anymore, and the only torque or factor that is still in the system is just gravity. And gravity here is just it's just going to just pull it down. Well, basically no, it's not going to pull it down, but if you move it here, the tangential gravity is going to come this way. Tangential gravity is going to come this way. And on here instead, tangential gravity actually tries to push you back down. Yeah, so I mean, it's kind of obvious, I guess. So here's this part, and then here is basically what I just said about everything. And one last part I want to say that is that we have a saddle node bifurcation at gamma equals to 1, which is quite obvious if we look at this change this way, and then to this, and then to this. And yeah, I mean, we see that there are no fixed points, and then there's a semi-stable fixed point popping out, and then we have two fixed points flying away, which is basically what happens on the saddle node bifurcation. And yeah, that's it. Thanks. 18 minutes. Go, God. Thanks for your attention, I guess.